Welcome back. Today, I'm going to be going over the concepts for factorials and permutations. Let's start with what a factorial is, and then we'll also, in a little bit, get into some practical applications of each one. So, factorial is of a number n is written as n factorial, right? So, n with the explanation point is n factorial, and this is the product of all the positive integers less than or equal to n. So, as an example, 5 factorial is 5 times 4 times 3 times 2 times 1. And if we multiply those out, we get 120. What about 3 factorial? Well, 3 factorial would just be 3 times 2 times 1, which is 6. These are some examples of the factorials. Now, I also want to get into actually how come we care? Like, how come the factorial is useful? Why would we care about what 5 times 4 times 3 times 2 times 1 is, or what 3 times 2 times 1 is in particular? Well, factorials are very useful for finding the number of ways we could possibly order a certain number of unique objects or people in a certain situation. So, for example, how many ways are there to line 5 people up at a bus stop? Well, according to this, 5 factorial ways is 120. So, therefore, there are 120 different ways that 5 people could line up at the bus stop. What about how many ways can 3 people line up at the bus stop? Well, according to this, 6 ways. There are 6 ways that 3 people can line up at a bus stop. Now, that said, how come that is, right? How come just putting a factorial on something tells us how many ways we could possibly arrange that number of objects or people into a straight line or into a specific order, for example? Well, here's why. Let's picture there's 5 people lining up at the bus stop. So here's my bus stop. And there's 5 people. One, two, three, four, five. There's the 5 spaces, and there's 5 people. Let's just call them A, B, C, D, and E. Well, how many possible people could line up in the first spot? Well, there's 5 people. It could be A, B, C, D, or E. So I'm going to write 5 here. Okay, how many people could line up in the second spot? Well, only 4 people now, because whoever lined up in the first spot can't also line up in the second spot. They already chose their spot, so they're set there. So now there's only 4 people who could line up in the second spot. Okay, now what about the third spot? There's only 3 people now because the person who's in the first spot already took their spot. Someone's already chosen the second spot as well, and so now there's only 3 people left. Okay, now that person 1, 2, and 3 have already lined up at the first 3 places, how many people could line up in the fourth spot? Well, just 2 left because 3 of these have already been crossed out. Okay, now that someone lined up there, how many ways are there for us to choose someone in the last spot? Well, just one last person because everyone else is already lined up, so whoever comes last just lines up last. And so we end up with 5 times 4 times 3 times 2 times 1, which is 5 factorial. And so that's why this is the case. I wanted to also explain how come this is the case, because my goal here with all of these, all of these presentations is not just to go over, here's the definition, so use it and take my word for it. The goal is to really understand it, to really understand why is this useful and how do we use this for, and why is this used for this particular concept. Okay, next let's talk about permutation. So, what's a permutation? A permutation is an arrangement of objects in a specific order, and in this case, the order of those objects does matter. Now, the difference between a factorial and permutation, because you might say, oh, but for factorial, in that example, the order matters as well. Well, with a permutation, we only are choosing a certain number of objects of the overall objects. So in this case of 5 factorial, there's 5 bus stop places in this example, and there's 5 people lining up at the bus stop. But what if I was to ask, okay, let's say that there's 20 people who live near enough to the bus stop to potentially go to it. How many ways could 2 of those people line up at the bus stop? Well, there's 2 steps to that. First, we have to choose which 2 people, right? So how many different combinations of 2 people are there? And then, okay, and when those 2 people get there, how many ways are there for those people to be arranged? So it's really kind of a 2-part question there to get to permutation, essentially. Here's a couple examples. Let's say that a teacher is going to randomly select 3 students from her class of 30 students to win a prize, but it matters what order you get picked in because it matters what prize you get. Maybe first prize is an all-inclusive vacation to Hawaii. That's probably the prize most people want. Let's say the second prize is a new computer. That's still great. I'm sure lots of people would still love to have a new computer, but probably not as good as a trip to Hawaii, although perhaps that could be debated. I'm not sure. The Hawaii trip certainly costs more, though, that's for sure. And let's say third prize is a pencil. Well, I'm sure you wouldn't mind getting a pencil, and that's certainly better than not getting anything at all, which is what the other 27 students in the class would get. But a pencil is not nearly as exciting as a trip to Hawaii or even a computer. A computer is probably a lot better than a pencil. And so the order does matter, right? Or even if the prizes were all of equal value, but they were different prizes, even then the order would matter because it still matters whether you're the first person picked randomly, the second person picked randomly, or the third person picked randomly, because you still care what prize you get, right? Choosing the same three names but in a different order would make a difference in this case. Whereas if all three people were getting the same prize, then this would not be a permutation because the order would not matter in that case. What's another example? Let's say that 20 people are competing for the first three prizes in the swimming competition, for example. And in that case, there are 20 potential people who could be picked for the first prize, or I guess you could earn first prize. Then after that, there's 19 people who could get second because someone already got first, and then there's 18 people left after first and second to finish the race who could possibly get third place. In that case, that's another example of permutations because although it would be an honor and a wonderful thing to get first, second, or third, all those are great. You know, order does matter, right? It does matter if you get first, second, or third, that's for sure, right? Let's move into combination. So a combination is the same as a permutation, except that order does not matter. So going back to the example of the teacher giving out prizes to three of the students, let's say the prizes are all the same. Let's say that whether you get picked first, second, or third, everybody gets a new computer. And it's the same new computer. It's not even three different computers because I know there's a wide range of computers out there. Let's say all three of the students who win get the same computer, and it's going to be, let's just say, MacBook Pro and the exact same one, exact same color, same everything. In that case, do you really care if you get chosen first, second, or third? Well, no, because if A, B, and C get picked, regardless of what order they get picked in, it's still the same three students getting the exact same prize. It's still the same combination. Whereas if there were different prizes, then the order would matter. That would determine what prizes students got, and that would be back to permutation again. One more example of a combination before I move on is that let's say that we have my daughter has 10 toys that I could possibly pack for her trip. And I'm going to pack 3 of those toys. How many combinations of 3 toys could I pack? That would be combinations because whether I choose the teddy bear first or the teddy bear last, for example, I still chose the teddy bear. Maybe the 3 toys I chose are the teddy bear, the cat, and a baseball. I'm not sure. Just trying to make up 3 toys, right? Whatever order I pack those 3 in, I'm still packing the same 3 toys, and so it doesn't matter. That's the same combination. But we want to know out of the 10 toys, how many ways are there to choose 3 different toys? And so if I swap one or multiple of those toys out for other toys, well, then it's a different combination in that case. But switching the order of the same 3 toys doesn't actually change anything in this scenario, which is why it's a combination. So the main thing to ask yourself to know, okay, is this a combination versus a permutation, is does the order matter or do we not care about the order, right? That's the question you want to ask yourself. Okay, let's move on to the formula. So here we already have the factorial formula, and as a reminder, it's just n factorial is equal to n times n minus 1 times n minus 2, and so on until we get down to 1. For permutations, this is the formula, and this we have not seen before. So the way we would write this is P and then in brackets n comma r, where n is the total number of objects and r is the number of objects we're picking. Now I do use objects loosely because combinations can also apply to people as well, not necessarily like physical objects per se. So for example, let's say that a teacher is choosing 30 students, or sorry, a teacher has 30 students in her class and she's choosing 3 to win a prize and it's 3 different prizes. We would say P and then 30 here for N because there's 30 students overall and we're choosing three of them to win three different prizes, essentially, right? And then, so in this case, this would be 30 factorial over 30 minus 3 factorial, and that would be 30 factorial over 27 factorial. Now, keep in mind that 30 factorial is just 30 times 29 times 28 times 27 times 26 times 25, all the way till we get to 1. And 27 factorial is just 27 times 26 times 25 times 20, and so on, all the way down to 1. And so therefore, this is the equivalent of 30 times 29 times 28, and then times 27 factorial over 27 factorial, and so these cancel out. And so we're just left with 30 times 29 times 28. And this makes sense based on our context, right? The context of, well, how many students could possibly win first prize, right? We're picking from a pool of 30 students. We're randomly choosing somebody. Okay, let's say I chose someone. Okay, great. There's 30 possibilities that could have been picked. Now, assuming that the same student can't win twice, now there's 29 students left in the class who could get the second prize. And then I pick someone else. Okay, great. Let's set that aside. Now there's 28 students left, all hoping to get the third prize. And so this makes sense as to why that is, if we really break it down, of why it would be n factorial over n minus r factorial. Now let's talk about combinations and how this one is different. So let's say that the teacher now is going to do another draw a few months later with the same 30 students, and the teacher's randomly going to select 3 students, but this time they're all going to win the same prize. So now order doesn't matter. In that case, the only change we're going to make is we're going to have an r factorial here added to the denominator, which in this case, r factorial would be 3 factorial, or 3 times 2 times 1, which is 6. Now, why would we have that r factorial there, right? Because I don't just want you guys to memorize these equations. I want us to really understand why these are the equations, okay? So here we have 3 factorial in that denominator. And the reason for that is because there are 3 factorial different ways to arrange all those people, and whether it's any of those 3 factorial ways, it doesn't actually make a difference, right? Because in here we're accounting for the fact that order should matter, right? With the 30 times 29 times 28, but we have to divide by 3 factorial because actually the order doesn't matter. And so if it's the same 3 students picked, then they could be arranged in any of those 3 factorial ways, and it would be the same combination. And so that's why we're dividing by 3 factorial, or 6 in this case. Because let's say that the people who get selected are person A, person B, and person C. For the permutation one, it does matter what order those are in, but for combinations, it doesn't, right? I could scramble these up into all 6 different ways. I'll show all the 6 different ways we could write this. However, in permutations, all 6 of these ways are the exact same thing. In permutations, all 6 of these ways are 6 different potential ways that these people could be selected. Whereas in combinations, all of these are the exact same thing, because if first, second, and third prize are exactly the same in the combinations one, then all of these are the same. And so that's why we divide by 6, because whatever 3 people are picked, the order then doesn't matter, and any 3 people could be rearranged in these 6 ways. And so that's why we do that division. All right, well, that is it for this one. In the next video, we will actually be going over some examples rather than just going over definitions and talking about why they are the case. So I will see you for that one.